During Google Summer of Code 2020, I worked under John Griffiths and Rick Gerkin in modeling the Fitsu-Nagama model of spike generations and squid giant axons using a two-dimensional simplified version from the Hodgkin and Huxley model. We can describe the Fitsu-Nagama model using these two equations in figuring out how spike generation occurs in squid giant axons. Overall, the purpose of this project was to create a Boolean test in determining where points of stability lie using different parameter conditions. This Fitsu-Nagama model lets us um, lets us imagine neuronal dynamics using a circuit using resistance, voltage, and recovery variable defined by these equations. And by varying different parts of the parameter, we can see how the voltage and the recovery variable change over time, and figuring out where the differential of the voltage and the differential of the recovery variable, shown with dot u or dot w here, figuring out where those equal zero, we can find out where parts of the model are stable or unstable, and by comparing stability in different parts, we can create a Boolean test. So the Fitsu-Nagama model will generally look at through null-clines. These are null-clines methods of figuring out where parameters can change the stability and features of the model in phase space. Graphs like this one, in the phase portrait of the physiological state of the Fitsu-Nagama model, lets us vary different parameters and figure out how the membrane potential and the recovery variable differ from one another. We can look at points of stability and other features like the sinks and saddles of equilibria shown later. And overall, this project will be used to perform a Boolean test in comparing different parameter sets to see how stability changes and other features may change too. So in this notebook, we'll be looking at this sort of circuit diagram. The circuit diagram lets us use these concepts from physics and engineering in varying the currents as well as the voltage of different parts of the Fitsu-Nagama model. And this gives us a really, really straightforward way of computing how the potential or the voltage measured in U and the recovery variable in W change. Performing a simple differentiation, we can define the Fitsu-Nagama model using the null-clines shown here. du dt and dw dt can be defined using these equations, and figuring out where they equal zero will tell us where parts of the model are stable or unstable. Eventually, in the notebook, we'll be determining how the SciUnit software works in unit testing. So SciUnit being this software packaging library for testing how models fit data very easily, testing how models fit experimental data, or comparing different data sets using different models. We can just get a better idea of how modeling works in computational neuroscience. So varying the values of these three parameters, alpha, epsilon, and lambda, we can see how the null-clines of the Fitsu-Nagama model differ from one another. Now, the Jupyter IPython notebook gives you a very straightforward method way of doing this. These different steps of the notebook can be run one by one, shown here using pip install and other methods of installing the packages, then importing the modules, all in Python. The other functions give us, as described earlier, what we're looking for. The null-cline analysis lets us send in different parameter sets to see how U and W differ from one another. We can find fixed points, between the parameter sets to find the intersections of the U and W null-clines. So coming out to this graph here, we would want to find out where these null-clines intersect with one another and where points of stability lie and where other points lie. So from the null-cline analysis, we can use the integrated equations to figure out the time derivative of the U and W variables using SciPy array and all these neat little features in Python. So this function is the overall function for stimulating the model and running it, and or creating the simulation itself. So we can send different parameter sets through the model using different ranges of epsilon, gamma, and beta, and create the graphs as an output of this cell right here. The phase portrait of the Fitsu-Nagama model lets us see how these parameter sets change with one another. So the dynamic Fitsu-Nagama models give us an integrated Fitsu-Nagama trajectory, and putting these things together, we can actually send the parameter sets to each other, and keep this cell lets us see how what the equations are and how the stability or other features are calculated and analyzed. Sending these different arrays, we can compare two different data sets and create a data frame to see whether points are stable or points are unstable between these data sets as well. So this is a data frame of actually the two data sets put together. But for the Boolean test, we'd actually be wanting to compare the data sets individually. But this data frame actually This data frame actually gives us a good idea of everything we can look for. So using a similar method like this one of creating functions, creating data frames, and sending parameter sets through, we can generalize this method eventually for testing different models in different conditions. And using a straightforward Boolean test from SciUnit, there it is, figuring out whether points are stable or unstable between two different data sets. And again, this is actually comparing two different data frames, DF1 and DF2. So there are some neat ways to plot these things. These 3D plots give us an idea of where points of stability lie for different parameter ranges and where where the unstable points lie as well. But they're pretty hard to look at. So, oh, and this one gives the quality as well, whether we're looking at a sink or a saddle or what feature we're looking at. So heat maps are actually a much more effective way of um, of conveying this information. The next few cells of this of this IPython notebook set up the heat map so we can figure out whether points are stable or unstable. The heat map shown here tells us there it is between different parameter ranges a, epsilon, and lambda. We can figure out where points of stability lie.